Welcome to Physics 2211 Lab 4 Oscillation. Our first goal is to compare the predicted motion and the observed motion of a mass in both the x and y direction. Our second goal is to plot the energy changes that we compute for the change in kinetic energy, the change in gravitational potential energy, the change in spring potential energy, and the change in total energy. We find that the predicted and observed motions are similar on both axes, but more similar in the x-axis direction. The total change in energy is 0, and the change in other energy supports this. Okay, so some of our fundamental physics ideas. Newton's second law, the velocity update formula. We have derived this before to find Vf equals Vi plus F net over m times delta t. And then we can derive the position update formula, where Rf equals Ri plus V average times delta t. However, because the spring force is non-constant, we use Rf equals Ri plus Vf delta t, where Vf is the last velocity. We also need to understand the energy principle, where delta E equals the work surrounding plus Q. Kinetic energy equals 1/2 mv squared, gravitational potential energy equals mgh, and spring potential energy equals 1/2 ks squared, where s is the magnitude of L minus L naught. Our system consists of the Earth, the spring, and the mass. Therefore, we have nothing in our surroundings. So there is nothing to do work, so delta E system equals 0. Delta E system is going to equal delta K plus delta UG plus delta US equal to 0. Okay, let's look through our glow script code. Here we set our initial conditions. We are given that the mass of the ball is 0.402 kilograms. And then we use the position vector from our tracker data, and we set the initial velocity as 0. Our delta t is 1 over 210 because it is a multiple of the time interval between the time frames of the experiment, which is 10.5. Constants found from the video data. We need both Ks and L naught, which we can find using our video. First, we need to find the period. We find the average period of the oscillation by selecting two places on the graph that are a couple peaks apart. I chose 4 peaks. And we find that our period is 1.5433 seconds. Then we substitute that into our K formula, and we get that K equals 6.663 Newton meters. Then we use this K to find our L naught from the video. We know mg equals Ks because the F net equals 0, so they both equal each other. And mg equals K times L minus L naught. We expand that out, and we find that L naught is 0.109 meters. Here we set our L vector, our L hat, and our S. And then we set our energies. We know these as shown before. In the calculation loop, we're going to find our F of gravity, our F spring, F net, and then we use the F net to calculate the ball velocity and update the position. Our results show that the energy remains 0. The change in energy remains 0, which is good. That's what we want. That satisfies the energy principle. Our delta U spring and our delta U gravity balance each other out, as well as the kinetic energy. We see in our x position versus time graph that they're pretty similar, but our y position versus time graph does have some discrepancies. Some potential sources of error include not accounting for other forces such as drag forces, not accounting for other energies such as rotational kinetic energy or thermal energy, and not consistently marking the center of mass in our tracker analysis. What does this mean? Yes, the energy principle is satisfied. We see in the graph that the change in energy is 0 because the internal energies always balance each other out to 0 because they oscillate in opposite directions. Our average oscillation period for the x position is 1.646 seconds, and the average oscillation period for the y position is 1.532 seconds. The difference is 0.114 seconds. This difference could have an impact on the calculation of the spring constant K, the spring force, and spring potential energy. This difference could be caused by inaccuracies in data gathering, such as misplacement, center of mass, camera distortion, etc., or it could have been caused by the drag force.